I'll start transmitting. Just 1 second.
Okay.
Okay.
Okay. Good. So good afternoon, everyone. Good morning, Zach. That is 8:30 apparently. And today we are going to have a talk from Zach Vanderbosch. I think I'm pronouncing your name close enough. He was a graduate student at the University of Texas at Austin, and now he's a postdoctoral research associate at the Caltech, California Institute of Technology. He is studying variable white dwarfs with a focus on the discovery and characterization of white dwarfs exhibiting photometric variability due to transiting planetary debris or pulsations. So he's also interested in developing techniques to distinguish the different classes of white dwarf, variable white dwarfs, using large time domain surveys as Squeaky Transit Factory and the future LSST legacy survey of space and time. And today he's going to present a talk title, Proving the Time Domain Universe for Persistently Variable Stars, New Pulsating and Outbursting White Dwarfs from Gaia, ZTF, and SDSS. So you may start, Zach.
Thank you, Alejandra. Yeah, so thanks for having me here to talk today. And it's good to be talking to people who I've worked with a good bit as well along the way. And yeah, so I have a pretty deep interest in using time domain surveys to advance discovery of all types of variable white dwarfs that are currently in low supply. So that could be these transiting planetary debris systems, or it could be the less common varieties of pulsating white dwarfs. Today, I'm going to primarily focus on pulsating white dwarfs and what I've been doing to try and find those using time domain surveys, but also using Sloan Digital Sky Survey, which was sort of my first foray into finding these types of objects. Yeah, so I just got to Caltech. Most of this work I did while I was at University of Texas, and I have a long list of collaborators who helped me on all this. So I just want to say thank you right off the bat. But yeah, so in anticipation of perhaps having a wide audience, people who might not know exactly what white dwarfs are, how they form, and how they become pulsating stars, I'm just going to give a little bit of background on this topic. So the broad strokes of stellar evolution are that stars begin on the main sequence, burn through their core hydrogen as the cores contract and the star heats up in the center. They start to burn heavier elements, but for the vast majority of stars, like 95–97%, they can't burn any higher than helium, and they end up with a carbon-oxygen core. And once all of the outer layers of the stars are blown away and on the asymptotic giant branch phase, you're left with the core, which is what is over here. Let me get my laser pointer up. Okay. So yeah, this is essentially the temperature of a core as it is just born onto the white dwarf cooling track. Starts off really hot and really bright. This diagram here is what we typically refer to as the Hertzsprung-Russell diagram, showing luminosity on the y-axis and effective temperature on the x-axis, where right is cool and red and left is hot and blue. And once a white dwarf is born, its evolution is relatively simple. It just radiates away the heat that it's left with into space and cools over time. So after about 1 million years, it gets down to 50,000 Kelvin. 1 billion years, it's around 10,000 Kelvin. and so on. The coolest white dwarfs to date are around 4,000 degrees Kelvin. They've taken anywhere from 5 to 10 gigayears to get there. Because they're supported by electron degeneracy pressure, they are actually very compact objects with radii comparable to the Earth, but masses comparable to the Sun. Surface gravity is like 100,000 times what we experience here on Earth. And they've been used in a lot of really interesting ways throughout astrophysics. And they also come in a lot of different flavors. I'm just going to go through a few of the ones that I'll be referring to a bit today. These flavors or spectral types are classes that we lump white dwarfs into based off of the spectral features we observe. So the most common spectral type we see is what we call a DA, where you have a carbon-oxygen core which dominates the mass of the white dwarf, but then the outer layers are a thin helium shell and a thin hydrogen shell. And it's the thin hydrogen shell that we see from Earth as light escapes from the white dwarf. And the hydrogen there leaves this series of absorption lines, which we call the Balmer lines. And that's how we identify this as a DBA. In some cases, white dwarfs are hydrogen deficient. And depending on their temperature, you might see helium lines in the spectrum instead of hydrogen. And so we would call that a DB. But the spectral type can change as a function of temperature. So in some cases, as white dwarfs cool, their spectral features eventually disappear because they aren't hot enough to excite those atoms anymore. And we call these DCs. I might refer to a few more throughout this talk, and I'll briefly mention what I mean when I talk about them, but these are like the main types of spectral types that I'll be talking about today. So coming back to the Hertzsprung-Russell diagram, here's the cooling track of a white dwarf. And like I said earlier, their lives are pretty simple. They just cool throughout time. But within specific temperature ranges, they actually start doing something interesting. They start pulsating. And the temperature range of the pulsation region, what we call the instability strip, depends on what the atmosphere is composed of. So for the DAs, they pulsate between around 10 to 12,000 degrees. And we know of roughly 300 or so objects there. And the DBs, they pulsate at higher temperatures, around 20 to 30,000 degrees. And there we only know of around 28 currently. We know of fewer in that region because, for one, hydrogen deficient white dwarfs are just less common. And also at higher temperatures, white dwarfs cool a lot faster. So they speed through this region, its instability strip. The pulsations look like this in some cases, where you have sort of a complex series of rises and dips that can range from amplitudes of 1 to 20% and periods of 2 to 20 minutes. And these pulsations are useful for looking into the interiors of these stars and learning about how these stars might have formed or what kind of progenitor stars led to the creation of particular white dwarfs. So yeah, we can use white dwarf asteroseismology, which is the process of fitting the pulsations we observe with models. From this, we can learn about internal structure, composition. If we happen to find white dwarfs with really stable periods, then we can track those periods over long time spans to see how fast they're changing and compare those to cooling models. Also, with those really stable pulsations, we can possibly find extrasolar planets due to the planet causing the white dwarf to kind of move around a little bit in space, which would change how quickly the pulsations arrive here at Earth. So we can track the pulsation arrival time. It can also probe the physics of convection in these stars, since the convective layer on the surface is what we think drives the pulsations to observable amplitudes. And kind of in connection with cooling physics, some white dwarfs, well, actually all white dwarfs will eventually crystallize in their interiors, but the most massive white dwarfs will do it sooner. And some massive white dwarfs that pulsate might already have a significant fraction of their interiors crystallized. And if we can do asteroseismology with those, we can learn about their interior structures as well. All of this, however, is dependent on periods. And getting those periods is sometimes difficult. The tool we use typically is either the Fourier transform or the periodogram. We look for significant peaks that indicate frequencies or periods in the star. And if we can identify those based off of the spherical harmonic of the particular pulsation mode. What I mean by that is that these pulsations are kind of manifesting as temperature variations across the surface. And we can approximate those temperature variations pretty well using a spherical harmonic equation to describe the distribution of temperatures. And it's those spherical harmonics that we need in order to do really detailed white dwarf asteroseismology. The difficulty is you typically need a lot of data to get reliable mode identifications. This has been done with the Whole Earth Telescope originally, which is a global network of telescopes that tried to just continuously observe white dwarfs for weeks to really nail down the periods. More recently, there's been spacecraft like Kepler and now TESS that can get continuous observations from space. That has been really helpful for doing detailed white dwarf asteroseismology as well. But that's a pretty small fraction of all the pulsating white dwarfs we know. A lot of white dwarfs, sometimes you could observe them as long as you want, but they just don't have that many periods that are driven to observable amplitudes. So you can't really do much with those either, no matter how much data you have. So there's a lot of challenges involved with actually putting into practice these different asteroseismic tools to learn about white dwarfs. And it all eventually kind of connects back to how many of these sources do we know in the first place. So this is particularly important for objects that we currently don't know many of. So for instance, the DBVs, which are shown here on the left within their instability strips. So these red lines and blue lines kind of denote the cool and hot boundaries of the DB instability strip. And same thing over here, but with dashed lines for the hydrogen atmosphere DAs. And this plot is in surface gravity on the y-axis and effective temperature on the y on the x-axis. And while we know of a lot of DAs that pulsate, there are we don't know of a lot of DBs, and we also don't know of a lot of very massive DAs that could potentially be crystallized in their interiors. So I've been thinking about how can we efficiently find these rare types of pulsating white dwarfs so that we can start feeding them into the pipeline, whatever that may be, either putting them into TESS or we're trying to schedule a Whole Earth Telescope run if we wanted to detail asteroseismology or monitor their periods over a long chunk of time. Or in the case of the DBs, to just constrain the instability strip boundaries empirically with better statistics. So yeah, that's what I'm trying to work on with ZTF now, but have already been working on this with SDSS as well. Okay, so next I'm going to jump into some of the techniques that I've been using to try and identify these stars, starting with spectroscopic surveys, time domain surveys, and then using follow-up photometry, and in some cases spectroscopy to identify these. Then I'll come back to the pulsating helium atmosphere white dwarfs, and also talk a bit about some of the work I've been doing to find massive DAVs, and also some outbursting DBVs, which I'll come to later. If I have time at the end, which I'm not suspecting I will, but I put this up here in case y'all wanted to ask questions about it. But I've also been using these same techniques to identify variable stars to find transiting planetary debris. And I have some slides that I might get to at the end, but if not, feel free to ask me a question about it. So yeah, let's jump into white dwarf variability and how to find them. And white dwarfs can be variable for a lot of reasons, from pulsations to binarity to planetary systems and also rotation effects. I'm going to be focusing, of course, on the pulsations and also transiting debris if I can get to that. But a lot of these other sources can be kind of contaminate your data if it's not what you want to find. So I will mention these a bit throughout the talk to kind of mention how I might be trying to avoid them as I'm looking for either pulsators or transiting debris systems. All right, so probably the most common way that people have searched for pulsators in the past is to first get a spectrum of a white dwarf or some broadband photometry of the white dwarf, and then use those data sets to estimate the atmospheric parameters of the white dwarf. So in the case of spectroscopy, you would take all of the absorption lines you see, either hydrogen or helium. You would fit those lines with models, and from those fits derive effective temperature, surface gravity, or even abundances of particular elements that are in the white dwarf. And then you can pretty much do the same thing with broadband photometry. You take data from Sloan or from Pan-STARRS or Gaia, and you take another white dwarf model and fit it to the points you see, and again derive temperature, surface gravity. And from those temperatures, if you're looking for pulsating white dwarfs, it's pretty easy to tell if it's inside of an instability strip or not. And if it's inside, then it might be a pulsator, unless its temperature is really uncertain or something like that. But the other way we can find these is using these large-scale time domain surveys. So Gaia is the big one. I mean, everyone has probably used Gaia at this point to some degree. It's an all-sky survey, so it's really revolutionized our ability to find white dwarfs. Before Gaia, we knew of order like 50,000, and now we know of 360,000 white dwarfs. So a huge gain in our ability to discover these less common varieties of pulsators or transiting debris systems or whatever you might be interested in. And then there's also surveys like ZTF, which do as much of the sky as they can since they're ground-based. ZTF is northern, so it does everything above minus 25 degrees deck, and obtains a cadence of 2 to 3 nights for as much of the sky it can see, and sometimes more in specific regions of the galactic plane. And from this, we can also use their data to look for white dwarfs that might be variable in some way. But these are nice because they just have an incredible amount of data, and you really don't even need spectroscopy or photometry to get atmospheric parameters beforehand to find variable stars. So you can kind of do the search for variability first, and then fine-tune some parameters to target specific objects, which I'll kind of demonstrate that in a bit. But how this works is we are essentially defining an excess scatter metric. So in this plot on the left, all of the gray points that you see rising up from low magnitudes to high magnitudes on the right are essentially the photometric scatter from Gaia observations of all of the white dwarfs within 200 parsecs. As you would expect, there's a rise as a function of magnitude because the fainter stars just have more noise. And so we want to first detrend that, and we fit it with an exponential and remove it. Because what we are interested in is finding stars that have more excess than they should compared to stars of similar magnitude. So after we define something like a significance threshold, this gray line up here, we identify all these red points as candidates for stellar variability of some kind. And overplotted on that are a bunch of blue squares, which are a bunch of known pulsating white dwarfs. It says ZZ Ceti here, but it's actually, I think, a mixture of ZZ Cetis or DAVs and also DBVs. And when we convert this plot into a color magnitude diagram, which is similar to the Hertzsprung-Russell diagram that I showed before, you can see a lot of stars kind of the blue squares clumping in one region. These are all the ZZ Cetis, and a lot of the red points are kind of clumped there behind it. So this was our way of first identifying that this metric, this particular metric applied to the Gaia photometry, is helping us to identify pulsators pretty efficiently, just because they show variability in a region where we already know pulsators are found. And then there's these few blue squares up here, which are this handful of DBVs that are in the sample. There's not nearly as much of a defined clump of red points up here, which is somewhat expected just because DBVs are a little harder to find. But for sure, this metric is working in terms of identifying excess photometric scatter. And we can take this a step further with ZTF, because with Gaia, we don't have access to all the single epoch measurements that they take. It's just sort of a global uncertainty for all the measurements. But with ZTF, we have access to all the data, and we can apply a lot more metrics to it to try and distinguish different types of variability more efficiently. So in this plot, it's pretty much the same as the previous, except this time the gray points, which is the full sample, have already been detrended. So all the exponential behavior has been removed. And just the red points are shown here again as like the top 1% most variable stars in this Gaia plus ZTF cross-matched sample. And again, if you look at a log G T-effective diagram to see where all these top 1% objects are, the vast majority are in the ZZ Ceti instability strip, which again tells us this metric is working in terms of identifying variable sources. But there's also a lot of stuff outside the strip, which is all very interesting. Could be cataclysmic variables, rotators, transiting debris systems, eclipsing binaries, all sorts of stuff. So it's useful for finding variability beyond pulsators as well. And here's just sort of a little taste of some of the objects we find after we first apply these metrics to the Gaia and ZTF photometry, and then followed them up with observations from McDonald Observatory at high cadence to actually resolve what the variability is. So on the left is all the ZTF data for these objects spanning about 2 years. On the right is the McDonald, or in the middle is the McDonald photometry. And on the right are the periodograms for each object and each data set. So purple is for the ZTF data, black is for the McDonald data. And what this is kind of telling us is that the ZTF data, a lot of people, what they typically do is just a period search in the ZTF data. They don't use these excess scatter metrics. And a period search would certainly help you find objects like this one here, which has a really stable recurring signal. And you can see the peak in the ZTF periodogram, as well as the McDonald periodogram. But then there are the pulsating white dwarfs, like these bottom two objects, and the transiting debris system on top, where if you tried to find a significant period in the ZTF data, you would totally miss these sources. So this, and it even applies to this star, which appears very stable and monoperiodic. Apparently there is actually some incoherence in this period, which causes it to get washed out over time in the ZTF photometry. So having these excess scatter metrics really helpful for looking into the pulsators in particular and finding more of those. But also for these more exotic types of objects like the transiting planetary debris systems. And here's just a kind of a broad summary of a lot of the stuff that we've found using this method so far. So here again is a log-GT affected diagram with DA instability strip, DB instability strip on the left. And all the light blue points are just the top 1% most variable. We haven't identified what all of those are, so some of them don't have a classification yet. But for those that do, they have different colored points. So dark blue indicates some of the pulsators we found. These triangles indicate, or the diamonds indicate some of the transiting debris systems we found. And the squares over here, I think 3 of these were already previously known DBVs, but one of them is new. So and the stars are cataclysmic variables. So all sorts of stuff in here. From this point on, I'm just going to be focusing on the pulsating systems. But again, if you have questions about the transiting debris stuff at the end, feel free to ask. Okay, so moving on specifically to the helium atmosphere pulsating white dwarfs. So this probably looks familiar to Kepler because this is a figure from a paper that we submitted and is currently in review or in revision. So the first way that I went about trying to find more DBVs was by using catalogs of white dwarfs with atmospheric parameters derived from Sloan digital sky survey spectroscopy. So this plot is showing in gray a sample of those from, I think this is the Kester and Kepler 2015 sample. These little blue squares are showing all the previously known DBVs, and all the red circles are showing the stars that I observed from McDonald Observatory to search for pulsations. I think this is it. Yeah, so a total of 55 objects and something around like 250 hours of observing time at McDonald. If y'all are familiar with McDonald, it's one of my favorite places to be. We have like almost unlimited time on the 2.1 meter telescope there, so we can undertake projects like this. There's a lot of places where the telescopes are too competitive to do these types of targeted surveys. So the 2.1 meter was really a perfect telescope and a perfect instrument for this task. And this was the result of the survey. So we found 19 new DBVs from this survey. Here the light curves are on the left, the periodograms on the right, ordered from top to bottom by the decreasing period or increasing frequency of the dominant mode observed in the star. The magnitudes of these stars range from 17.3 to 19.3, which isn't necessarily ideal for like wanting to do more detailed observations. So maybe some of the brightest here you could do a bigger campaign with to really nail down the periods, but a lot of these systems are probably too faint to do stuff like that. But still, these systems are useful in other ways for primarily constraining the extent of the DBV instability strip, which has historically been really hard to pin down observationally. And this is sort of the current status based off of currently published DBVs. The blue and red lines are theoretical boundaries for the instability strip. And as you can see, the uncertainties in all these temperatures are pretty large, which is due to how insensitive the helium lines are at this temperature region to changes in temperature. So the lines pretty much stay the same strength throughout most of the instability strip, which makes it hard to get a good solution for these. Other issues are the possibility of trace hydrogen in the atmospheres of these stars, which if you don't detect it, you can only put an upper limit on it. If you assumed it was actually a pure helium atmosphere, you could be getting the temperature too hot by a few hundred degrees, or in worst case, sometimes a few thousand. But that's just sort of the best we can do. And I think the real way to tackle this is just by finding more. You're not going to really be able to improve the temperature uncertainties. So the next best thing you can do is just get more to improve your statistical constraints on this region. So here are the ones we've found added in, which brings the total to 45. I think I might have had this number wrong. This should be 28 instead of 26, but whatever. We're in the mid 40s now. And the statistical strengths are better, but I think we're still hoping to maybe increase the number a little bit, especially towards the edges, because that's what really helps define the instability strip. And the blue edge in particular is rather poorly defined, even with 2 more objects that we found. But the NOVs we find, so NOVs are the objects we observe but don't find any signs of variability. Those are helpful as well for putting constraints on the boundaries of the instability strip. In this version of the instability strip, we're finding that the empirical temperature at the red edge is about 1,000 to 2,000 degrees cooler than what theory predicts. And on the blue side, there's this one object, PGO112, which is still challenging the blue edge as well. And these are important constraints to have because they help us determine the efficiency of convection throughout the instability strip. And that ties into other physical processes, such as diffusion timescales of metals. And so it'd be really good to keep improving these constraints. Something that complicates this is how you treat convection in these stars. So what I've just done here is apply recently calculated 3D convective corrections to the temperatures and the surface gravities of the stars, which actually appear to bring the observed red edge into better agreement with the with the theoretical red edge. But there's still the issue of if you reuse temperatures from different works. So most of these temperatures come from SDSS related catalogs, but some come from other works that used different instruments, different telescopes. All those systematics end up getting put into this, and also whatever code you use to fit your model atmospheres to the spectra of these stars can affect that as well. And if you were to use a different catalog to define the instability strip, it would look like this. It's a pretty big difference compared to what I just showed previously. So I think the real way to tackle this is to do sort of one homogeneous spectroscopic survey as many objects as we can, and then compare instability strips between a lot of different catalogs to try and put some constraints on the extrinsic uncertainties in the surface, in the atmospheric parameters for these stars. It's something that I've been working on. So I've been getting some spectra from the Hobby Eberly telescope at McDonald for as many of these systems as possible. So that is a project that's in the works, but somewhat further down the pipeline. But just having more systems for the moment is good. And it does put some more statistical constraints on the boundaries. Okay, so what are the next steps for finding these? I'm interested in using time domain survey data to find more of everything that we need to find more of, essentially. And so I mentioned previously that we've used these variability metrics to discover all sorts of variable white dwarfs. But I was talking about it in a very global sense. So I took like the entire white dwarf catalog from Gentile Fusilo's paper and ran it through this pipeline of variability metrics. But because the ZZ-SETIs really dominate when you do a global search for variability, it's actually best to try and, if you're looking for a specific type of variable stars elsewhere, it's better to cut the ZZ-SETIs out as best you can. So here's an attempt at doing that. On the left is the Gaia color magnitude diagram again. And this blue box here just defines a region where I'm searching for variable stars. So any objects outside of this blue box are not being considered in this analysis. And this blue box was just empirically defined by these orange circles, which are all of the known DBVs with parallax uncertainties greater than or less than 10%. So those help define the region that I should be looking in. And after selecting those and running the same sort of variability metric pipeline on these, this is the result of that on the bottom right. So again, here's sort of the trended objects running along 0, and then a sort of significance threshold shown higher up. All the red points are stars that are potentially variable, and the blue squares are some of the known DBVs in this sample. And the green stars are objects that I've followed up since doing this and found to pulsate. And there's one that's not on this plot, so there's actually 6 of those. So it seems to be a pretty effective way to find these, and you don't need any information about whether it's a DA or a DB beforehand, because these metrics are so reliable at finding variable stars. There is some contamination in here, so like a few of these are going to be rotating DAs, magnetic DAs, or some sort of peculiar white dwarf. So there is contamination in here that's not pulsating DBVs, but it's relatively small, and those objects might be interesting on their own. And it's definitely better than trying to compete with the large cloud of ZZ-SETIs if you were to do this globally. So here's the 6 new DBVs that have resulted from looking or identifying candidates with ZTF. And the most notable thing about these is that a lot of them are actually quite bright. So 5 out of 6 have magnitudes less than 17. And this is really just the result of looking at more of the sky. So from using SDSS spectroscopy, you're really limited to just a smaller fraction of the sky, because SDSS wasn't an all sky survey. So now that we have ZTF and Gaia, we can actually do all sky searches for pulsating white dwarfs. And a lot of those are actually going to be pretty bright just because we haven't even known about them before. So yeah, I think this is an exciting avenue to go if you actually want to find white dwarfs. It would be good for more detailed asteroseismic analysis. For instance, some of these we have submitted for TESS observations, so we'll actually have like really good, or at least better constraints on the periods and these systems, and maybe even get good mode identifications out of these. The last thing I just want to quickly mention is that I've also been using this to look for really high mass DBVs as well. So stars that are sort of down here inside of this orange circle. And at this point, we have found 3 that are greater than 1.1 solar masses and seem to have rather interesting looking light curves. I don't know if I have a plot of the light curves here with me. No, I don't think I do. But these could potentially be used if the pulsations are stable enough over time to see, to do p-dot measurements of the pulsation periods. Especially this one, if it's, these are photometric temperatures from Gaia, so they are very uncertain. And I'm in the process of getting spectra for these that can better constrain their atmospheric parameters. But this one is enticing, even though the uncertainty is huge. If it is this hot, then it would be the hottest ultramassive pulsating white dwarf we know of to date, which is exciting because we can the pulsation periods might be more stable than they would be at lower effective temperatures. Okay, so now I want to move on and talk a little bit about outbursting white dwarfs and how we've been able to search for these in ZTF as well. So outbursting white dwarfs have primarily been found by Kepler mission and the K2 mission due to the fact that they can observe continuously for long periods of time. These outbursts recur very infrequently, so they're hard to detect from the ground. And it was really only with the advent of Kepler that we started to understand what these are. So here's what an outbursting system looks like. This is an outbursting DA or DAV. So in the black regions, that's what we call quiescence. This is where the white dwarf is just sort of pulsating normally. But every few days or weeks, there are these large mean flux increases in the star, each of them lasting 2 to 20 hours and recurring kind of semi-regularly on some time scale, but the spacing between them is also quite erratic sometimes. And if you zoom in on one of these outbursts, you can see that during an outburst, the pulsation amplitudes also get a lot larger. Another characteristic of these is that they tend to be found near the red edge of the instability strip for the DAs. The sort of thinking behind this is that at these lower effective temperatures, there's a higher density of pulsation modes in the stars. And the most, I guess like the most likely mechanism for this that's currently been discussed is a coupling between some of these pulsation modes and even lower frequency daughter modes that you don't observe in the star. And when there's a resonant coupling between these, there's a transfer of energy that causes a lot of energy to flow into the convective layer of the star, producing the outburst we see. At least that's sort of the model or the idea behind what might be happening here. And a few years ago, we observed an outburst from the ground for the first time. It was a totally serendipitous thing in a star that we really shouldn't have even found this in, which I'll explain in a bit. But we found it on this one particular night. The mean flux increased by about 30%, which corresponds to an effective temperature of increase of around 4,700 Kelvin. And this is in a DBV, whose quiescent temperature is around 24,500 degrees Kelvin. That is a huge change, which pushes the object pretty much to the blue edge, if not slightly beyond it. And so what we think might happen here is the convection zone on the surface of the star just completely disappears. And so after this really large outburst event, the star is pretty quiet because it's taking some time for the convection zone to grow back and for the pulsation modes to grow in or up to observable amplitudes again. So the reason this we really shouldn't have seen this is because Kepler observed this star 3 different times in 3 different campaigns for a total of, I think, like 200 days of observing where no outburst was detected. So the odds that we actually saw one when we looked at it from the ground are pretty low, surprisingly low. But it's just one of those lucky things. But I tried to quantify just how, like, the lack of a detection here tells us something about the recurrence time, because at the moment we only know of 1 outburst that has ever happened in this star. So it's hard to put any constraint on the recurrence time if that was the only data we had. But since we have all this non-detection data, you can put some constraints on the recurrence time by sort of testing a variety of recurrence periods and modeling some light curves to see how, like, whether they would be detected in those campaigns based off of a specific recurrence time. The red line is like a simplistic model where you assume every campaign there's an equal chance of observing an outburst. And that gives you sort of a smooth function in non-detection probability as a function of recurrence time. So essentially, shorter recurrence times are much easier to detect, and longer ones are much harder to detect, which is pretty obvious. But if you do it a little more complex and you test a wide variety of sort of like phases of the phases of the orbits and test some like random orientations of the orbits and sort of like random spacings between each outburst, you end up getting a slightly more complex pattern showing that some periods are a little bit more likely than others below 200 days, but that kind of smooths out as you go to longer and longer recurrence times. But sort of the takeaway from this is that most recurrence times below around 300 days, or about a year, are would only be detected 50% of the time or so. So this helps put some constraint on what the recurrence time might be. It's still not well constrained, obviously, but it just sort of asks the question, what ranges of recurrence times could we see in these types of outbursting systems? What ranges of amplitudes of outbursts could we see? And this is, I think, something that ZTF could try to answer, which I'll get to in a bit. But here's a little bit more data on this system, showing sort of the characteristics of it. The top 3 sort of inverted periodograms are from the different Kepler campaigns. And you can see primarily they have power at low frequency, close to 1,000 microhertz. But there are some narrow peaks located here and at slightly higher frequencies as well. On the bottom are all the ground-based data periodograms, where the red lines indicate data taken out of outbursts, so in quiescence, and the blue shaded periodogram is from the one night that was during the outburst event. And what's really striking about it is that in quiescence, all of the observed pulsation power from the ground lines up with the low frequency power observed by Kepler, but during the outburst, the power shifts dramatically to higher frequencies. Without the Kepler data, we would have presumed that these pulsation periods sort of like came out of nowhere. But in fact, they're always in the star, just at lower amplitude and harder to detect. So this helps us build a picture of what's going on here that during the outburst, the convection zone is likely thinning or even completely disappearing. The convection zone, even though it drives amplitudes, it also damps the amplitudes of pulsations, especially for higher frequency pulsation modes. So when it thins very dramatically like that, it makes sense to suddenly see these higher frequency modes at very high amplitudes because the damping effect of the convective layer has disappeared. So we got lucky one more time, actually. We found another outbursting DBV just with, well, we were following it up from McDonald, trying to characterize the periodicities in quiescence. So here's a night couple before, a light curve a couple nights before the outburst, and then a light curve about a month later. And even though the light curve during the outburst is really short, you can see that its mean flux is elevated, which is not something you would expect to see in any just regular pulsating white dwarf. And also the periods have gotten much shorter. It looks much more squished together. And this was actually validated or verified by ZTF observations as well, which is these 4 points over here. So we're pretty confident that this is the third known outbursting DBV. The first known is actually sort of a kind of a funny story because it was observed back in the 1990s and called the Sforzando, and we didn't know exactly what had happened. But we noted very similar characteristics were noted during the Sforzando as what we now know happens during outbursts. So in hindsight, I think the first outburst was probably from GE358, which is why I call this one, these two, the second and the third. And here's the instability strip with all of the known outbursting DBVs shown over here and the known outbursting DAVs shown over here. And we're building up a pretty similar picture in the DBV side as well, that these outbursts tend to happen sort of in a smaller range of temperatures. They aren't just happening all across the instability strip, or at least the ones we detect easiest are happening in a smaller range of temperatures. And the last thing I want to say about the outbursters is some stuff I found with ZTF. It's pretty interesting. So there's these three objects. These are their ZTF light curves, and like the full ZTF light curve on the left, and then a very zoomed in portion on this these flux increase events. So at first, I would have looked at these and thought this is some kind of stellar flare due to like sort of the fast rise and slow decay that you see in pretty much all of these. But what's interesting about these systems is that they all have something in common. They're all pulsating white dwarfs. None of them have an infrared excess indicating the presence of a flaring companion. They all have temperatures around 11,000 degrees Kelvin, where you would expect to find outbursting white dwarfs. And they all, the largest, I guess, those are the things they have in common, which makes it seem like maybe the same mechanism is causing these outbursts in each of these. But what's really surprising is that the largest outburst here has an outburst, a total outburst energy of 10 to the 36 erg, which is 2 to 3 orders of magnitude larger than what we've seen so far from K2 and Kepler. So potentially we are, we can use ZTF to probe how big these outbursts can actually get. I think some work still needs to be done on these to figure out, or to completely rule out the possibility of a companion. But so far, these look like isolated pulsating white dwarfs that sit right on top of all the other outbursting white dwarfs that have huge outburst amplitudes. But as you can see, there's only one in each of them. which kind of fits with the paradigm of the bigger the outburst, the bigger the recurrence time in these types of systems. But it'd be nice to see more, because with some of the observing facilities at Caltech, we can essentially cue telescopes robotically on events like this and get spectroscopy or photometry within minutes to hours of one of these events happening. So hopefully something like this happens again, if not in these systems, perhaps others. Yeah, that's pretty much the end. I'll just conclude there. So yeah, variable white dwarf stars can be pretty efficiently identified using these time domain surveys. I think spectroscopic surveys are still very relevant in finding these, especially as SDSS 5 is ramping up and getting spectroscopy in the southern hemisphere as well. That's still going to be an efficient way to find these. But the time domain surveys coming out now just add on to that capability as well. And not just for pulsating stars, but all rare types of variable stars. And yeah, working on the DBVs in particular is helping to really bring them closer to their full potential in terms of asteroseismology, better constraining the DB instability strip. But there's still a lot of work that needs to be done on that in terms of doing like a really good systematic analysis of the extrinsic uncertainties in their atmospheric parameters, and adding a homogeneous spectroscopic survey to that would be good. And yeah, hopefully we can use ZTF to try and probe these outbursting systems to higher energies and higher recurrence timescales than we've currently been able to do with Kepler. So yeah, I guess that's pretty much it. I won't go into any of the transiting debris stuff, but if you have questions, I'll happily take them.
Okay, thank you, Zach. For the people following us on YouTube, we are going to stop streaming now, and we thank you for your presence, and we expect you next week for our next